This morning, I asked my Tesla to drive me around and wanted to see how long it could make it before I had to take over. The car drove for over an hour and a half, 34 out of 34 miles, entirely on FSD, with zero human driving, and there were zero takeovers whatsoever. This is truly incredible. It was almost like an autonomous experience, and I have to salute the autopilot team for this. It was jaw dropping. Here's the full, raw, uncut video so you can see it for yourself if you don't believe me.
Great. Thank you so much for the introduction. Hi, everyone. My name is Ashok Heliswamy. I work at Tesla on the autopilot team. Hopefully, you're able to hear my voice and see my screen and video and things. Please let me know if that's not the case. Great. Yeah, today I would like to present our work on what we think is going to be the foundation model for autonomy and robotics. This is not just the work of myself. I'm representing a large team of talented engineers in our team. Let's get started. Our team has shipped the full self-driving beta software to everyone who has purchased it in the United States and Canada. There's roughly 400,000 vehicles, and today they have driven up to 250 million miles on FSD Beta. I think the cool thing about this is that this is a scalable self-driving stack that you can take the car anywhere to the US, turn it on, put it in a destination, and the car would attempt to navigate to the destination, handling all of the like turns, stopping at traffic lights, interacting with other objects. And all of this is driven primarily by the 8 cameras that are on the car that are giving a full 360-degree coverage around the car. The reason that works well is because our stack is based on really modern machine learning based stack where a lot of the components of the self-driving stack are just folded into neural networks. And I would say this is different than the more traditional approach to self-driving, which uses a localization, maps, a lot of radar, ultrasonics, etc., to fuse together. Instead, this is primarily being driven by just cameras. And if you have a Tesla yourself, you can obviously buy the car and experience it. Otherwise, you just to take my word or look at some videos, but it works quite well. And we are in the process of making it even better. I shared about these occupancy networks that are one of the more important pieces in our stack. I would consider this as one of the foundational model tasks because this is very general. This is a very general task and doesn't have any specific ontology. Or like at least robust to ontology errors. It really just predicts whether some voxel in 3D space is occupied or not, and the probability of that. And can hence represent arbitrary scenes. There is no labeling or ontology design required, and it's quite general and can apply like anywhere. And in addition to just the occupancy, we also predict the flow of voxels in the future that kind of like gives arbitrary motion as well, and everything runs in real time. This is quite similar to NERF in general, but unlike NERF or say multi-view reconstruction, which is usually done for a single scene, we predict the occupancy based on the 8 cameras in real time. So the videos stream in, and then we just predict for all of space around the car on whether this voxel is occupied or not, as opposed to like doing this offline post-processing step. So architecture looks with a lot of, it looks very complicated, but then it's actually not that complicated in the end. Videos from multiple cameras stream in, and you can choose whatever backbone you want, RegNets, whatever the latest bits, you can throw anything in there. And then everything comes together in a large transformer block that does sort of a spatial attention to build up features, and also does temporal attention with some like geometry thrown in there to form some features that can then be upsampled into the actual predictions. It's quite straightforward, even though the diagram looks a bit complicated. And the same architecture and the modeling can be used not just for occupancy, but for other tasks that are needed for driving. Obviously, lanes and roads are very important for driving tasks, but I'd say lanes are quite obnoxious to predict. The reason is, first of all, lanes are higher dimensional objects, unlike it's definitely not like 1D or 2D, like, high dimensional. And then they have like a graph structure. Like objects, for the most part, like say vehicles, they're self-contained, they're just, local. Whereas like lanes can span the entire road. You can see multiple miles of lanes in your view, and they can fork and merge and cause all kinds of trouble in the modeling. They also have large uncertainty. Sometimes you might not be able to like view the lanes because they're occluded, or it's nighttime, only part of the lane is visible. And it's not just that. Sometimes even if everything is visible, even humans cannot agree on whether something that you're looking at is 2 lanes or 1 lane, for instance. So there's a ton of uncertainty in like what are lanes. And then it's not sufficient to just predict them as some kind of raster. It's very hard to use downstream then. So it's better to predict them as some kind of vector representation, like polylines, splines, polynomials, etc., to help with ease of use. And all of this needs to happen within tens of milliseconds in real time. Like I said, it's like a very difficult problem to predict lanes in real time in the real world. Nonetheless, we use state-of-the-art generative modeling techniques. In this case, we use autoregressive transformers, quite similar to, I would say, GPT, in terms of how we model the lanes. So we can predict you can tokenize the lanes and then predict them 1 token at a time. Unlike language, which is mostly linear, we have to predict the full graph structure. Hence, we come back, predict what is the forking point, what is the merging point, etc. And everything is done end to end using neural networks with little to no post-processing required after this. Another important task for self-driving is obviously moving objects, vehicles, trucks, pedestrians, what have you. And it's not sufficient to just detect them. You need to have their full kinematic state, and also predict their shape information, their futures, etc. All of these models, the models that I described earlier, even the lanes one and objects one, are in some ways multimodal models, in the sense that they take in not just camera video streams, they also take in other inputs, such as, in this case, ego's own kinematics. So ego's velocity, acceleration, jerk, etc., all goes in. We also provide in the navigation instructions to the lanes to kind of guide us where to, like which lane to use, etc. So everything is done within the network. That's why I say it's like a modern machine learning stack, where instead of doing this in post-processing, we just try to combine everything and then do perception sort of end-to-end, so to speak. So here you can see predictions of these models. The lanes that you see here, the vehicles that you see here are all just predicted, again, by these networks without a lot of post-processing. There is no tracking or anything like that in the things that you're seeing here. So overall, I would say that's quite stable. The green spines that are coming out of these vehicles or just their forecasted future, it's kind of like a standard task at this point, I would say. But it all works quite nicely and in real time in the car. It doesn't have to stop with just perception too. Once we have all of these percepts, like lanes, occupancy, objects, and even a few more like traffic controls and other things, you can do the entire motion planning, also using just a network. I won't go into too many details on like how we do that, but essentially, it can just be thought of as like one more task instead of it being a separate thing. So how is all of this possible? And I think it's because we have built this sophisticated auto labeling pipeline that gives us data from the entire fleet. Millions of video clips across the entire world can be tapped. On the left side, what you're seeing is an example of multi-trip reconstruction, where we choose some location, multiple Tesla vehicles driving through the location, upload their video clips and other vehicle kinematic data to us. We bring everything together and reconstruct the entire 3D scene. So the polylines that you look, there's a cyan colored one. There's also a few other colored ones. Those are all different cars doing different trips through the world, and it's actually all very well aligned. Let me see if I can play it again. Yeah. The pink line and the cyan line that you see there, those are like different trips of different cars driving around, and everything is just aligned very nicely. And this multi-trip reconstruction has enabled us to, get all the lanes, road lines, everything directly from the fleet in the millions, anywhere on Earth, essentially. Once you have this like base structure of trajectories, calibration from all these cameras, you can really do a lot of cool things to reconstruct the entire scene. I'm not sure if the video plays quite nicely, but in my own screen, it looks very smooth, where you can see the ground surface. It's reconstructed quite nicely. There's like no artifacts such as double vision or blurring. Things are like crisp, look like geometric. They are correct. This is a hybrid approach to NERV and general 3D reconstruction. Sometimes in NERV, even though the re-rendered visuals might look very nice, the underlying geometry might be very fuzzy and cloudy. So we have a hybrid approach, which works quite nicely. You can see here, the barriers, the vehicles, even trucks, etc., are reconstructed pretty accurately. Once we have these reconstructions, we then run even more neural networks just offline to produce the labels that we want. Like I had mentioned earlier, for lanes, we need some kind of vector representation to make it very easy to use. So instead of just using raster directly, take rasters, we have offline neural networks that run on top of it and then produce the vector representation that can be then used as labels for the online stack. Similar to the lanes, like once you have the lanes and the roads reconstructed, you can also auto-label traffic lights. Here you're seeing traffic lights auto-labeled by your system without any human inputs. And these are all like multi-view consistent. Let me try to play it again. Yeah, we can predict their shape, color, relevancy. You can see this white traffic lights on the side. They also reproject correctly into all the camera views. And it's because we have this really good auto labeling system that calibrates everything jointly and it's like pixel perfect in 3D space. So yeah, all of these predictions together give us super solid understanding of the world from cameras. And I would already try to call this, sort of a foundation model that can be used in a lot of different places. And these predictions really help FSD, drive in any place. Like you don't have to geo-restrict it. You can, even sometimes construct a new road, turn it on, and it would work quite nicely there. In addition, they also help manual driving, obviously, because humans are not perfect drivers, so they need some help every now and then. In this case, on the left side, the ego driver, for some reason, blew past the stop sign and was almost about to crash into this red car. And our system, detected this and then braked automatically. And similar on the right side, driving straight, and then someone just comes in and then cuts us off. It's quite dangerous, but then the system applied the brake quite early. The reason why this is different than what you would think that AV systems have been there for since 1980s. What is new about this? I think Tesla is the first company to ship this emergency braking for crossing vehicles, to the best of my knowledge. And the reason that crossing objects are harder, unlike say vehicles that are in your own lane, is because for crossing objects, you need to know whether they're going to stop in time or not. What is the stop line? Do they have traffic lights? And if they were to turn, which lanes would they turn into, etc. There's a ton of work that needs to happen to understand where the crossing objects would go and likely to go. Do they have room to stop, etc. It's not as simple as just directing a vehicle and having the velocities and things like those. Yeah, so like I said, I think I believe Tesla is the first company to ship crossing AB, and it's already in customers' hands in the last several months. But is the foundation model really just a bunch of these tasks concatenated together, or can there be more to it? We think there can be more to it. These tasks, like in the occupancy, for example, while it's quite general, some things are harder to represent even in that space. I'll probably go to more details shortly. So that's why we are working on learning a more general world model that can really just represent arbitrary things. So in this case, what we do is we have a neural network that can be conditioned on the past or other things to predict the future. And obviously, everyone has wanted to work on this forever. And I think with the recent rise in generative models like transformers, diffusion, etc., we finally have a shot at it. So what you're seeing here is purely generated video sequences. Given the past videos, the network predicts some sample from the future, hopefully the most likely sample. And you can see that it is being predicted not just for one camera, but it predicts all the 8 cameras around the car jointly. And you can see how the car colors are consistent across the cameras. The motion of objects is consistent in 3D, even though we have not explicitly asked it to do anything in 3D or not even baked in any 3D priors. This is just the network understanding depth and motion on its own without us informing it of so. And since this is all just predicting future, RGB values, the ontology is quite general. You can like throw any video clip from driving or from YouTube or from your own phone. Anything can be used to train this general dynamics model of the world. Additionally, it can also be action conditioned. We can show a few examples. So here on the left side, the car is driving in the lane, and we're asking it to, okay, just keep in this lane and keep driving. And then, like I said earlier, the car is able to, or the model is able to predict all of this geometry flow by very nicely and understands 3D. On the right here, we're asking it to change lanes to the right side. Maybe we'll go back and play it again. So on the left, it's just going straight. And we ask it to go straight, the model goes straight. And then on the right side, we ask it to make a lane change, and it makes a lane change. And the past context is the same for both of these outputs. So given the same past, and when we ask it for different futures, the model is able to produce or like imagine different futures. This is super powerful because now you have essentially a neural network simulator that can simulate different futures based on different actions. And unlike a traditional game simulator, this is way more powerful because it can represent things that are very hard to describe in an explicit system. I'll show a few more examples, but then it is super powerful. And also the motion, the intention, and then the natural behavior of other objects, such as vehicles, is very hard to represent explicitly, but in this world, it's very easy to represent. It doesn't have to stop with just RGB. You can obviously do this kind of future prediction task, not just in RGB, but also in panoptic segmentation, or you can extend it to also 3D spaces, where you can imagine future 3D scenes entirely based on just the past, and then your action prompting, or even without prompting, you can predict different futures. This is, personally, I'm amazed by how well this works, and it's a very exciting future that we are working on here. Yeah, here's some examples where I think something like this is going to be needed to represent like what's happening in the scene. Like there's a lot of smoke coming in one of the pictures. Like there's paper flying everywhere. That's going to be tough for even occupancy, where okay, you have paper flying everywhere. There's occupancy flow, but then how do you know it's paper? What do you know the material properties of it? There's like smoke. Obviously, you can drive through it, but it is occupying space, and light does not transmit through. There's a lot of nuances to driving, and we have to really solve all of these problems to build a general driving stack that can drive anywhere in the world and be human-like, might be fast, efficient at all speeds, yet very safe. And I think we're working on the right recipe for building this. And obviously, training all these models takes a ton of compute, and that's why Tesla is aiming to become a world leader in compute. Dojo is our training hardware that we have custom built at Tesla that is starting production next month, essentially. And with that, we think we are on the way to become one of the top compute platforms in the entire world. And we also think that to train these foundational models for vision, we need a lot of compute, and not just compute for training this one model, but compute to try a lot of different experiments to see which models actually work well. And that's why it's super exciting for us to be in this spot where compute is going to be abundant, and it's just going to be bounded by ideas of engineers. The thought is this is not just being built for the car, but also for the robot. We already have the occupancy networks, for example, and a few other networks all shared between the car and the robot. And it actually works quite well and generalizes across these platforms. And we want to extend it to all the tasks that we have. Even like lanes and vehicles, for example, should not be specific to cars. If the robot, say, happens to walk to the road and looks around, it should understand roads and vehicles and how vehicles move, etc. All of this are just be built for both the platforms, and any other future robotics platform that would also need this. That's basically it. To summarize again, we're building this super cool foundational models for vision that really understands everything. And it should generalize across cars and robots. It's going to be trained on tons of diverse data from the fleet, on tons of compute. Yeah, so I'm really excited for the next 12 to 18 months of what's going to happen here. Thank you. Happy to answer any questions.
We have actually quite some time for questions. So if you have a question, you can come forward. Otherwise, I can start with one from the Zoom chat. And it's actually about the 3D reconstruction with your hybrid nerve approach. And the question there is, how can you actually deal with moving objects in this formulation?
We can really just track, moving objects. There's a lot of cues that the object is moving with respect to the scene, and we can also extract that information to segment moving things separately. Obviously, for things that we know can usually move, it's very easy, like vehicles, trucks, etc. Those are very easy because we already know that these objects can move. But arbitrary things such as flying trash bins or what have you, you can use a lot of other signals in the data itself to help do it.
Hi, yeah. Can you share a little bit more details about the world model? For example, is it similar to like VQ-GAN tokenizer and then autoregressive on top of those tokens, or mask-it, or any sort of details you can share?
I'd say still it's like work in progress. I don't think we don't have to over fixate on the current architecture. I think it's just the main message is that these kind of future prediction tasks are starting to work now. And that gives both like a simulator where we can roll out different outcomes, but also learn representations just by making this prediction. I think that is the key message.
Hi, thanks for the enlightening talk. I have a minor question. I really looking into the details. I noticed that when you predict the lines or lanes, something like that, you use the autoregressive models. I wonder why is the logic behind this, the choice of autoregression instead of just simultaneously predict everything at once? Could you please illustrate the logic here?
Sure. Like you mentioned, lanes can like fork and merge and do other things, and there's a graph structure to them. And you can predict them simultaneously, and it's like hard to, like it is we want to model a distribution over high dimensional space, right? Because like if there's uncertainty on like whether it's like one lane or two lane, you don't want to predict like 1.5 lanes. We want to either predict one lane or we want to predict two lanes. So we want a sample from the distribution. There's some distribution that okay, maybe 60% probability it's like one lane and 40% probability it's two lanes. If you predict it without like a proper generative model which gives nice samples, you will get sort of like smear, and then everything will look blurry. And it's very hard to then use downstream. So that's why it's useful to, do something like this to get a nice sample.
Thanks for the great presentation. I have some questions regarding the technical details. So I want to take a look at the visualization of the occupancy network output. Looks like it's a 3D voxel. And I have a question about the actual voxel size, and do we change the voxel size in near field and the long range?
Yeah, again, these are like hyperparameters. Anyone can try with different voxel sizes. It's really a trade-off between memory and compute and what you're willing to do. So that these are not set in stone. It's not whatever the application needs. Even between the robot and the car, you can like configure different sizes, and they have different needs. So it is really configurable, and optionally can be made queryable, as in you can get like arbitrary position by just having the network emit small MLPs or something like that, where you can query to arbitrary position. Again, it just comes at compute. So it's up to the design of the downstream tasks to determine, what is the base size, you need these MLPs or not, and you get away with like some simpler formulations. It's really up to, there's like large design space here.
Thank you for the awesome talk, Ashok. So I have one question regarding the general model, word model you just mentioned. How would that actually apply to the humanoid task, for example, manipulation? What kind of methods you use to make that generalized from autonomous driving to the other humanoid robotics tasks?
Yeah, I think the same should apply for humanoid robot in the sense that you can prompt it to do arbitrary things. You can ask it to pick up a cup or walk to some door or something, and then the model should be able to imagine what picking up a cup would look like or walking to a door would look like. And I don't see why it should be any different between the car and the robot. So because it's all pixels and the shapes are all the same, so it's just going to be a video that looks like the hand is reaching to a cup, or the robot. If it's a first person view, then it's a first person view of the robot, walking to the door. Like that's, I think it should work.
Okay, thank you for your presentation. You presented us a lot of individual modules. I would like to know if you could share us more details, how you will unify those modules into the end-to-end system in the FSD 12. For instance, how the occupancy could be used in the end-to-end system.
Yeah, the occupancy is already used for a lot of collision avoidance. Sometimes when there's like some strange vehicles, say like there's construction vehicles that are have their like lever arms like going like this and then can pick up things, and it's very hard to model using say cuboids or something like that, and you can obviously represent it with meshes, but then they become these high dimensional objects. Then distribution over them is pretty hard, and the occupancy is like a slightly, I would say, low level or like a dumber task where you can just like predict whether something is present and like where it is moving, and that is already enough to avoid collisions. And we make sure that the planning system respects collision avoidance from the occupancy.
Sure. Thank you for the wonderful presentation. I really enjoyed it. I'm very curious about your general world model. So I'm like a big fan of Tesla, and I want to know like what's like the inference times for this model. Can I expect to see it on a car anytime soon? Yeah.
Only thing I can say is that it hasn't shipped to customers yet, and we are still optimizing it. Maybe later this year. I don't know.
Oh, sorry. Yeah, I saw in your architecture you didn't have the map component fusion step in your model. Is it gone now, or if it's still there, then how do you deal with like alignment issue with your? Because you're not using HD map, right? So when you fuse the map information with your perception information, like how do you deal with that in the fusion process?
Sure. Yeah, I think these are not HD maps, so the alignment is not super critical in some sense. You can have 20 meters of error or like 50 meters of error and still fine. It's really just what you would look at at your phone or something when you use navigation. Your Google Maps or whatever map application you use might give you some route and like represent this, and that is enough to kind of tell the network where we want to go. So it's really like low definition maps. And it is intentionally designed that way so that we don't take a large dependence on the maps. It's really just to roughly guide which roads we should take, which lanes to pick and things like those.
Okay, so our next keynote speaker is Phil Duan from Tesla. So Phil Duan is a senior staff software engineer at Tesla. So he leads the autopilot team for occupancy network, object detection, behavior prediction, auto labeling, and online perception. So today's talk title of Phil is Building Vision Foundation Models for Autonomous Driving. So let's welcome Phil.
Let me figure out the hardest part of the presentation. Sorry. Okay. All right. Thanks for the introduction. I'm very excited to be here with you guys to share some of the progress we have made on Tesla Autopilot for the past few months. So for those of you who are, okay, let me actually hide this. Anyway. For those of you who are not familiar with Autopilot, this is a self-driving feature building for all the Teslas made in the world since about 2016. And the features range from basic autopilot, which has like lane keeping, vehicle following, to what we call a navigate autopilot, which works on highway for lane changes, follow the route, take forks, to our most advanced software package called full self-driving. And this basically takes you from a point A to point B with no human interventions at all. And this is the video from one of our customers driving in San Francisco. As you can see that it is capable of navigate through a complicated city, taking turns, yield pedestrians and traffic signs. And the uniqueness about our approach is that we are very famous for doing this with vision only. So all this is done with just 8 cameras around the car, provides 360-degree field of view. And these cameras runs on 36 frames per second, and it processed by 144 teraops of compute in our car. And we also do not use any additional sensor and HD maps whatsoever. And this works, anywhere in the world for basic autopilot, and it works for full self-driving with North America, including Vancouver. So, if you go to a Tesla store today, buy a car, you can do this yourself. And currently we have about 400,000 cars driving with the full self-driving software. And cumulatively, they have driven more than 250 million miles. So you can see that it's like a lot of data coming from the fleet. And for all the other cars, autopilot is always running in the background, even though it's even when human was driving. So we provide a activity safety feature for things such as automatic emergency brake. So when human makes a mistake, the autopilot will try to take over and protect the safety. And besides that, autopilot also runs in the background to collect more data to help us to build our neural networks. So so there are roughly about 3-4 million cars running in the world today to do this data collection. And you can think about these are robots on wheels. So besides autopilot, start about 2 years ago, we also started to make a humanoid Tesla bot called Optimus. So this is the basically in a humanoid form factor. It has a very impressive hardware platform, 200+ degree frame body control. It is built for a general purpose robotics application. And as you can see that the robot obviously has a completely different form factor than the cars, but we were able to leverage a lot of lessons we learned to build the cars, build the compute, and build the software to bootstrap this project. And the bots are basically, rubbers on legs, and as I said, it shares a lot of stuff from the car. One example, it is that it shares the same compute platform. So this is the in-house built FSD computer chip with a 144 teraops per second compute, and this runs all the Teslas in the world, and also is used to power the robots. And because we have the same computer platform, it's also fairly straightforward for us to build the same AI software stack. So the Optimus and the Autopilot software team, we work very close together. We share the same repo, and when we build the computer vision models, we try to leverage things so that we don't have to build 2 separate applications. And this also kind of enforces us. Whenever we build new software, we have to think about, how do we build something that is foundational, that can be shared among the 2 applications. So one of the network I can mention is the occupancy network. I think ties pretty well with the challenge we have later in the workshop. So we effectively have the same network running on both the bot and the car with just a little bit of tweaking where, certain things are more relevant to cars and certain things are more relevant to the bots. Even though it is a completely different environment, outdoor versus indoor, we're able to actually kind of build a network from like exact the same model with just a little bit, data difference. And I think we showed this occupancy network the first time at a CPR last year. And since then, we're kind of very excited to see how the research community has reacted to this. We have seen all kinds of different variations of this coming out. There's also challenging with hundreds of people participating. And I'm definitely very excited to see where this is going next. But for those of you who are not familiar with this, I'll just do a quick recap on this. What the occupancy network does for us is that it takes all 8 cameras image video stream in and produce a single unified volumetric occupancy in vector space directly. It has video context, and for each point in the 3D space, we predict whether it is occupied or not. And because of the video context, we are able to reason about occlusions and predict the things are behind visibility region. And the blue contour showed earlier here briefly was the way we use to model the volumetric visibility. And it also has a dynamic resolution. As you can see from the video here, certain voxels are bigger than the others. I will go to more details later. And for each of the voxels, we also predict semantics as color coded here, such as curbs, cars, static, road debris. Those semantics are usually defined for more driving relevant classes. And as you can see, for Optimus robot, we'll use kind of a different set of semantics. It also produces occupancy flow for motion. Since this network is very generalized, it does not make any assumptions on the object shape or motion. So it is able to capture arbitrary motion such as a swerving trainer here. And this network right now runs in all Teslas in the world with the FSD computer, and it's incredibly efficient in memory and compute. Runs about every 10 milliseconds with our it also helps with latency, able to remove ISP in the loop, and it is we don't even do any tone mapping at all, and all the images generated here are actually done post-processed just for human eyes. We take these images and we rectify that with the camera calibration, and we then feed these rectified images into a set of RegNets and BFTNs to extract multi-level image features. Then we construct a set of 3D position queries along with the image space features as keys and values, and we feed them into an attention module. The output of the attention module is some high-dimensional spatial features. And we align the spatial features with vehicle odometry to create, to capture motion. And this is kind of like a simplified here, but it's a lot of work done happening here to just make sure the vehicle odometry is done correctly to recreate what happened in the car and to align the features precisely. So, and after we do this, we're able to create a very rich spatial and temporal features, which we then pass through a set of deconvolutions to provide the final output for the volume, which include the occupancy flow, semantics, and so on and so forth. But the output of this volume is in a fixed sized voxel grid, which is not precise enough for control. As you know that, when things are close by, you have to really know these dimensions very precisely, and things are farther away, probably does not matter that much. And the way we solve this problem is that we also predict feature maps on a per voxel basis. And then we feed it into those per voxel feature maps into a set of MLP practice with a set of 3D positional queries. So as the output of the network, we can query any 3D positions around the car to get the output. So after knowing the model better, let's look at one more video. Here we have an articulated bus parked on the side of the street, illustrated by the red L here. As we get closer, the bus starts to move. As you can see, the front of the bus turns blue first, indicating the model is predicting non-zero velocity. And as the bus keeps moving, you can see the whole thing turns blue, and you can see a very nice shape capture the motion and the position of the bus. So this is kind of like a awkward task for traditional object detection, because you have to figure out, okay, what's the formulation? Do I use 1 or 2 cuboid to represent this bus? But for occupancy network, it does not matter. All we care about is what is visible and what is the motion. So our car will be able to actually handle and yield to this bus correctly. Besides this voxel gray, we also predict surface output. And the surface has both 3D geometry as well as semantics. So by semantics, I mean we also capture the color of the surface and all the road markings on surface, whether it's a stop line, lane lines, or like any yield signs, stop signs that are on the ground. We found this to be incredibly helpful for driving in unusual driving environment, such as San Francisco, which has a lot of hilly road and curvy road, where knowing what the surface looks like in 3D space removes the flat world assumption, and we found that incredibly improve our driving smoothness. So, and the surface or the volume are actually not output separately. In fact, the volume output is actually aligned with the surface implicitly, so that when you go through a different surface area, the voxels does not move up and down. It always just aligns with the drivable surface. And as we can see from this video here, the car is going through a hillcrest area. You can see this 3D shape of the surface very nicely, and it aligns with the voxel grid as well. So we can use this for a lot of different things. For example, the planner can use this information to decide how fast we should be driving here, and also it helps us to reason about occlusions, because sometimes the occlusion is not really due to any obstacle; it's just because the lack of surface as the surface is like going down. So we kind of built this network, and it runs in the car for about, I think, probably almost 2 years now. And then it works very well. So we start to think, what else can we build on top of this? So early this year, we had this very fun project where we start to predict a distance field around the car on top of the occupancy network. So this is literally just put a small head on top of the network and do a regression test to get a distance field. And we then show this distance field on UI for customers as a manual driving feature for parking or maneuver through very narrow area. And this is the video with one of our customers doing a parallel parking. And you can see from the right side that this contour is generated by this distance field. So compared to like traditionally, usually this is done with ultrasonics, right? So we just most of cars have ultrasonics on the front, on the back, and trying to just measure the distance directly. And the advantage here is that first we have 360-degree coverage. Let me just play this video one more time. And then it also is able to capture the obstacles at different height, because we don't have this sensor limitation. So for example, the curb, and ultrasonics is usually pretty bad with S-curve detection. And third is that it covers arbitrary range, right? So we don't have like a range limit from the ultrasonic sensor anymore, and it's able to basically capture according to as large as what we want from the occupancy network, and we just show as a range that is comfortable for the driver to use. So this vision-based park assist is just a small application. But while working on this, we realized that this model actually has really rich features that's able to capture a lot of things going around us. And so we start to think, okay, how can we leverage this and build a really strong world model? So if you zoom out a little bit and look at this network, right? So the bulk of the network, all it does is really just create this world model in the vector space features. And this kind of ties to the previous talk where, we really want to just build like a really nice 4D world model to understand the world. And once we do that, all the downstream tasks are actually just tiny heads that is very easy. And we can just like plug in, do some fine tune on that. It usually just works very well. I couldn't find a very nice picture to capture this, so I just put a Tesla logo there to represent the vector space features. So, but what we're really looking for from this direction is really just like how do we build this 4D space world model feature, and then we can just use that to capture everything we want for driving, for humanoid robot, or for anything that related to embodied AI. And if we do this correctly, we'll be able to use this feature to capture everything that is relevant for driving, whether it is the aforementioned, a volume or surface, which has, all the information we need for understanding where to go, and for objects, for lanes, and for traffic control. And instead of trying to build different models to tackle each one separately, we really want to just like build one model that does everything together. And traditionally, we shared a lot of features from image space, which just extract the 2D information. That information is actually not quite enough for doing this kind of foundation model. And now, since then, we have changed our approach to actually combine everything in vector space, so that we just need to build one model that does everything very well, and then then connect them with different tasks for downstream applications. And in order to train such a big model, obviously you need tons of data. So we are very proud that we built this very mature data engine in the past few years. And this, in my opinion, is one of the biggest advantages we have here. So what do we do here, if you start from the bottom, is that whenever we have a model, we deploy it to the car, and then we mine the model with millions of Teslas on the road. And we mine mostly to two things. First is that we use heuristics to detect things that happen very rarely, so we can get the data back and then feed that into our network. The second is that we also run this compared to what a human does. So to understand that, okay, what is the inconsistency here? What did our model do wrong so that the human made a different decision? And once we have this event trigger, we put this data back, and then we automatically label this data to generate this beautiful ground truths in 3D space, and then we use to train this model. And we call this approach fleet learning, basically learn everything from our fleet. And most of the work happening at Tesla Autopilot is actually just crank this data engine and get the fleet learning going. And we have engineers looking at data all the time, and arguably spend more time on data than the model. And give some examples of data. We showed this video at AI Day last year, which shows how we leverage all the fleet from all the Tesla vehicles from the same intersection. We put them together to reconstruct the 3D surface and the lanes jointly, which we'll be able to actually create a ground truth neighbors that much better than if we were just to do that with a single trip. You can see all the lanes are very consistent across different videos, across different trips. And then we feed this data into our network to train our lane network. And the good thing about this is that our customer drives the Tesla in all kinds of different locations, and we get data mostly from the places where with a lot of Teslas. And guess what? That's also the area we care the most about. So we can immediately feed this data back to our training and train a network, deploy to the car, and the customer will just have a much better model because of their driving. And this year we extended this same approach. Besides lanes, we start to model everything. So this is a 3D reconstruction from multiple trips of Teslas in the same area, and we put together. All this is generated from 8 cameras of video streams, and we put together through different trips. And you can see that it's able to capture all this very high quality information, and we can use that to train all kinds of stuff to make sure the world is consistent. And all this data is very rich in terms of that. We don't have a separate data set just to provide one ground truth anymore. We just have a unified data set that captures everything we need to train such a foundation model. And besides the data quality and the quantity, the other thing that really matters is data diversity, right? So if you only have, boring data, this thing will rarely work. So this is also one of our biggest advantage where we can get those data back from fleet. So this is just some examples of the random Tesla customer driving. So I will just pause for a second that you guys to see what kind of crazy scenarios we can see here. A lot of the stuff is, when you will rarely run into in real life, but once you, aggregate over 4 million cars, it actually weird stuff happens every single day. And what we do here is that we put this data back and put in the data engine directly and run the auto-enabling pipeline, fit into the data set and the model training. Once you put all this stuff together, you'll be able to just build a very large, highly diversified, highly quality data set, and we use the trade foundation model. And in our opinion, this is the path forward to build a foundation model for autonomous driving, and as well as eventually the whole embodied AI. This work presented here is done by dozens of very talented engineers at Tesla Autopilot. It's my privilege to present on their behalf. And if you guys are interested in this, please consider joining us. Thank you.
Any questions from audience? Yeah.
I know that Elon Musk has claimed that we will have end-to-end system in the FSD 12, right? And I would like to know how the occupancy network you have mentioned can be changed or even fit to this kind of end-to-end system.
Yeah, so that's a good question. Yeah, so basically we're building this network. So it's not really an occupancy network anymore, right? So we're basically building this foundation model to capture this world model, and we think that will be essential to use for end-to-end driving. And as for the end-to-end driving application itself, we're not ready to show what we have done so far yet. And I guess stay tuned.
Okay, so you just mentioned, so probably occupancy network is mainly used for building the foundation models, but not used in the end-to-end system.
Exactly. Yeah. Yeah.
Hey, thanks for the nice talk. How do you compare attention, self-attention or cross-attention based occupancy estimation with traditional multi-view stereo? So like
I would say that a big fan of Transformers. So, and we've definitely tried the different approaches, and the Transformers just like works amazingly well. And it is also very resistant in terms of, I'm a big fan of like learn-based stuff where the information will extract more implicitly, where for different cars, when you do multi-view geometry, it is like usually a very deep like uphill battle in order to get every tiny bit of the geometry detail correct, so that you can build everything and correctly. And this kind of stuff just works much better, in my opinion, with the attention module, which goes to play well with our strengths of a huge amount of data. When you learn from most data, the model just learns it very nicely.
Cool. Thank you.
Hello, thanks. Thank you for your wonderful speaking. And I have two questions. The first is, what do you think the problem of occupancy network? I have talked to many researchers. They think the occupancy network are too dense. The feature or something are too dense and too heavy to do, and every disadvantage of segment model, the occupancy model also shares the disadvantage. So what do you think the problem or disadvantages of the network of the occupancy network, and then there is a question too, and what is the next after occupancy network? Yeah, I have to.
Yeah. So there are basically quite a lot of different representations for like this occupancy, right? So we use kind of dense voxel gray, and you know, you can also do any other representation, implicitly, SDF, this kind of stuff. So the as I described in the slide, basically we have this dynamic resolution thing, which is a way to help us to make the network actually small enough to run in real time, right? So we don't just like naively say, okay, we need X centimeter resolution, so we have to segment the entire world in such thing, which is obviously not scalable. So I would say that the dynamic resolution thing we did here is one of the main reasons that we're able to actually achieve a high perception performance while running incredibly fast and efficient. And a lot of advantage we have is also with our own neural net accelerator. Basically, we build in-house so that we're able to actually accelerate this with what we need. And I kind of just said that in like one sentence, but it's an incredible amount of work actually happening in the background just to make this thing run fast enough in the car.
Okay, thank you. So what's the next? Is there any idea?
Yeah, so the next idea is that I would say that basically the occupancy thing is really just like building these features for the world model. We eventually it's not gonna like, I don't think we'll explicitly be driving on top of that. So these features give us this 4D understanding of the world. And I think the next steps, a lot of the next steps will be really just like on the application level. How do we derive different applications in a very lightweighted way to represent different scenarios?
Okay, thank you.
Yeah, hi, Fias. Thanks for the great talk. So like, people are now very confident in the foundation models, especially after ChatGPT comes and solve everything. So people are like more and more confident in these foundation models, especially how they will solve the autonomous driving task. So I'm curious about like, how can you quantify the data distribution for the foundation model in a driving task? Like as you mentioned, there are many factors in the driving, like dynamic mode, static object, and also the lane factors and the different classes. So as you mentioned, like when you get more data, you will determine whether the data is real in our current data, and we fit into our model. So I'm curious about how can you quantify whether the current data is real, or how whether the data is valuable for the retraining of our model. Yeah.
Yeah, that's a good question. Yeah, so I guess the data is basically used for whatever we need, right? So what we do is that we build a very good, there's two, I would say there are two sets of this for this. First is that we have a very complicated eval system to actually capture what is actually required for driving, right? So basically we're not building data for the sake of building data. We're building this data set to address problems. So we need to really measure our progress in terms of different scenarios so that we know which one is working well, which one is not working well. And sorry, I lost my channel, sorry. And on the flip side, it's also like there's like this scaling law basically has proven to be very well done with the language model community, right? So what we also look at is that we're applying scaling law to video module as well, right? So to vision models. So how do we basically build a model at what point the model the data is big enough, right? And whether data is about like or model is about like, right? So obviously because this runs in an embedded system in real time, so you cannot just naively scale up the model. So usually what we do is that we basically figure out what the model, what is the best size of the model that is running in a car, and then we scale that according to data, according to compute, and according to different parameters to figure out what is the best combination. And while doing that, usually it gives us a very good idea about how the data quantity and distribution.
Yes, thanks for the answer.
Thank you.
Thanks for the great talk. So I have some questions regarding deploying transformers on vehicle. So actually transformers, we have like we basically find transformers are much more difficult to actually deploy. We are not just talking about academic here. We're actually talking about engineering, and to build a product, actually you need to make everything real time on the vehicle, and the hardware perf is. I think transformer operators create a lot of difficulties here. I'm pretty sure you. So I wonder if you could share some insight, and also I wonder because right now, at least for camera-based perception, a lot of the state-of-the-art research were also purely CNN based. So when you are building the product at Tesla, do you find that actually there are cases or there are insights where there are something that CNN simply cannot do the same good job as transformer, that you are willing to pay the cost for deploying the transformers? So maybe generalization at scale, or maybe some others. That's my question. Yeah, thank you.
Yeah, so absolutely, deploying transformer is not very straightforward, I would say. So we actually goes to the previous question where we have an in-house neural net accelerator, which actually gives us a lot of advantage, because when we build this chip, we don't have to worry about somebody else has to use this chip, right? We only build this for our own application, which obviously transformer is a big part of that. So we have a very good deployment team actually work very hard on how to optimize this for deployment. And so far, I think initially it was quite challenging, but once we get working, it actually runs incredibly fast with our computer. And we also did a bunch of study for CNN versus transformer as well. And for us, it's that we're not we don't really worry too much about the philosophical debate of CNN versus transformer. We just use whatever runs fast and also does the job. And transformers obviously scale very well with the number of parameters, right? But we are because it's a real-time system, so we're also not going that route to just go from that. And when the parameter counts are lower, sometimes certain CNN actually does better than transformer. I think highlighting complex, for example. And we definitely kind of try to take advantage of both and put together to build such a network.
Thank you.
Thanks for the talk. I'm just talking a little about some challenges for generating occupancy map right there.
Mm-hmm.
So I guess I saw there you consider some night vision or some low light vision considered right there. But I'm just wondering if you consider some adverse weather conditions and contaminations on the sensor or something like that. Then that make it very challenging to generate accuracy map right there.
Absolutely, yes. So those are definitely the most challenging scenarios for us, right? So basically our customers drive everywhere, and a lot of places at different season with very challenging scenarios. I think I probably have seen more adversarial weather events probably than anybody in the room here, just all over the world, and we have to deal with all that. And on one side, that the fortunate thing we have is that we have tons of data from those, and we're able to actually targeting those problems specifically, solve them one by one. On the other side, definitely on the modeling side and the ground truth generative side, I would say most of the work is actually spent on dealing with such scenarios. And the normal sunny day driving scenario is actually quite straightforward to do. We usually don't have any engineer in the loop. You get a clip back, you run, it just works. And most of the time and the effort we're spending on is actually for all these adversarial scenarios.
Is that on Tesla, understanding about how to tackle, how to deal with that weather condition right there? Are you still studying about that part for FSD?
Yeah.
So now you are developing that to handle those kind of bad challenge condition right there.
Yeah. I mean, so what we do is that the ones we already, for example, you can drive FSD in snowing days, in foggy days, for example, it works just fine. And we also we gradually move to even, there's always long tail events we'll try to solve, right? So if you drive Tesla, you'll notice that sometimes it will tell you whether it's degraded, so certain functionality is not working as well as expected. So that is also very important to have a good understanding of what you are capable of doing and what you are not capable of doing, and to ensure the safety. And in the long run, obviously we'll have to solve all this problem.
Thanks.
Hi, in your demo, it seems that you created the ground truth, and it seems that only the static objects are created. Do you create the ground truth of the moving objects?
Yes, absolutely. Well, moving objects is a big part of the driving. Yeah, we'll have that too.
It seems that creating the ground truth of moving objects is difficult. Could you explain how the difference of the creating process?
Yeah. So I guess it's a bit of a history here where when we started, we only do moving objects, right? Because those are more relevant for driving. And so we actually, I think it's a fairly common approach among all community that how we model moving object. We started by just doing a cuboid, right? Just like fit every car into a box, and then but then gradually we realized the problems such as the articulate bus ones were shown here. So we had to actually model the exact shape of the objects. And a lot of them are done basically through what we call offline tracker. Basically, we take all the videos back from our cars and then we process offline to figure out what is going on. So that usually involve three different things. First is that we have kind of like traditional robotics algorithm to use to help process the temporal information. Second is that because you have future information available offline, right, you're able to go forward and backward to actually create a ground truth that is much better than what you see in the car in real time. The third is that we also build large offline models to do this. So the models we use to run the offline ground truth generation is especially for moving object are much bigger than one we run in the car because it runs offline. We're actually able to do that. So usually, so that's the way how we get a really good ground truth for moving objects.
Thank you.
Yes, I'm very excited to be here. Thank you for the introduction. I would like to talk a bit more about what Tesla has been up to over the last few months. So first to start, I guess we are here at the CVPR workshop on autonomous driving. So I think I'm preaching to the choir a little bit, but I'd like to start with some slides on like why we're doing all of this. And I think, unfortunately, we're kind of like in a bad shape when it comes to transportation in society. And basically the issue is that we have these metallic objects traveling incredibly quickly and with very high kinetic energy. And we are putting meat in the control loop into the system. And so this is quite undesirable. And really fundamentally what it comes down to is people are not very good at driving. They get into a lot of trouble and accidents. They don't want to drive. And also, in terms of economics, we are involving people in transportation. And of course, we'd like to automate transportation and really reap the benefits of that automation in society. So we all, I think, are on the same page that it should be possible to replace the meat computer with a silicon computer and get a lot of benefits out of it in terms of safety and convenience and economics. So in particular, silicon computers have significantly lower latencies. They have 360-degree situational awareness. They are fully attentive and never check their Instagram and alleviate all of the issues that I presented. And so I think this is not super shocking, and a lot of people have been kind of really looking forward to this kind of a future. This is a frame from iRobot, a really good movie if you haven't seen it. And here, Will Smith is about to drive a car manually. And this other person here is shocked that this is going to happen. This is ridiculous. Like, why would you actually have a human driving cars? And so I think this is not very far from truth. And this movie is taking place in 2035. So I think by then, I actually think this is a pretty prescient prediction. So what I think is kind of unique about Tesla and in our approach to autonomy is that we take a very incremental approach towards this problem. So in particular, we already have customers with the Autopilot package, and we have millions of cars, and the Autopilot software is always running and providing active safety features, and of course, the Autopilot functionality. So we provide additional safety and convenience to our customers today, and also the team is working on full self-driving ability. So I would briefly like to very quickly speak to the value today that we provide, just to give you some examples of what the team is up to and what we're sort of doing today. So here's an automatic emergency braking scenario. So the driver here is proceeding through an intersection, and you can see trouble coming here. So the person kind of crept up from here, and the car sees the pedestrian, object detection kicks in, and we slam on the brakes, and we avert collision. Here's an example of a traffic control warning. So this person is probably not paying attention, potentially on the phone, is not braking for the traffic lights ahead, but we see that these are relevant traffic lights. They are red, and we beep, and the person immediately starts slowing, and probably does not actually enter the intersection. These are examples from pedal misapplication mitigation, PMM. Here, a person is unparking from their driving spot, and they are trying to turn, and then they mess up and they accidentally floor it. So they floor it right there, and the system kicks in, it sees pedestrians ahead of us, and it slams on the brakes and averts what would be a very gnarly situation in this case. Here's another last scenario I can show briefly. So this person is trying to park, and they turn to the right here, and they intend to press the brake, but they actually floor it. And the system again sees that there's no driving path forward and actually slams on the brakes and averts. In this case, this person is not going to be swimming in this river imminently. So these are some examples of the value that we are providing today in this incremental autonomy fashion. But of course, the team is actually sorry about that. The team is working primarily on the FSD functionality, which is our full self-driving suite. So here we have we have the FSD Beta product, and it's in the hands of about 2,000 customers. And this is an example from one of the customers driving around San Francisco. And these people are posting videos on YouTube, so you can check out a lot of videos. But what we're showing here on the instrument cluster is we're showing all of our predictions. So you're seeing some road edges, some lines, some objects, and the car, of course, is navigating around autonomously here in San Francisco environment. Now, we, of course, drive this extensively as engineers. So it's actually fairly routine for us to have zero intervention drives, I would say, in like sparsely populated areas like Palo Alto and so on. I would say we definitely struggle a lot more in very adversarial environments like San Francisco. A lot of people working in autonomy, of course, know all about that as well. So this drive ends up being a fairly long drive, and it's zero interventions in this case. Now, one thing I like to point out always whenever I show the video of Tesla driving around autonomously in these city environments is you've seen this before, and you've seen it for a decade or more. So here's a Waymo taking a left at an intersection. And this is actually a pretty old video, I believe. And so you've been seeing stuff like this for a very long time. So what is the big deal? Why is this impressive? And so on. And I think the important thing to realize, and that I like to always stress, is that even though these two scenarios look the same, so there's a car taking a left at an intersection, under the hood, and in terms of the scalability of the system, things are incredibly different. So in particular, a lot of the competing approaches in the industry take this LiDAR plus HD map approach. And so the idea is that you take an expensive sensor, a LiDAR, on the top of the car, and it basically gives you range finding around the vehicle in 360 and gives you a point cloud. And what you have to do is you have to pre-map the environment with the LiDAR sensor, and you have to create a high definition map. And then you have to insert all of the lanes and how they connect and all the traffic lights and where they are. And you basically have to create a high definition map. And then at test time, you are simply localizing to that map to drive around. And so the approach we take is vision-based primarily. So everything that happens for the first time there in the car based on the videos from the 8 cameras that surround the car. And so we come to an intersection for the very first time, and we have to figure out where are the lanes, how do they connect, where are the traffic lights, which ones are relevant, what traffic lights control what lanes. Everything is happening at that time on that car, and we don't have too much high definition sort of information at all. And this is actually a significantly more scalable approach, because if our product is on a scale of millions of customers on Earth, and so it's actually quite unscalable to actually collect, build, and maintain these high definition LiDAR maps. It would be incredibly expensive to keep this infrastructure up to date. And so we take the vision-based approach, which of course is much more difficult because you actually have to get neural networks that function incredibly well based on the videos. But once you actually get that to work, it's a general vision system and can in principle be deployed anywhere on Earth. So that's really the problem that we are solving. Now, in terms of the cartoon diagram of a typical sensing suite of an autonomous vehicle, these are kind of like the typical sensors you would see. And as I mentioned, we do not use high definition maps, and we do not use LiDAR. We only use video cameras. And in fact, the vision system that we have been building over the last few years has been getting so incredibly good that it's kind of leaving a lot of the other sensors in the dust. And so actually, the cameras are doing most of the heavy lifting in terms of the perception that you've seen in the car. And actually, it's gotten to the point that we are able to start removing some of the other sensors because they are just becoming these crutches that you start to not really need at all. So actually 3 weeks ago, we started to ship cars that have no radar at all. So we've deleted the radar, and we are driving on vision alone in these cars. And the reason we are doing this, I think, is well expressed by Elon in this tweet. He's saying, when radar and vision disagree, which one do you believe? Vision has much more precision, so better to double down on vision than do sensor fusion. And what he's referring to is basically like vision is getting to the point where the sensor is like 100x better than, say, radar. then if you have a sensor that is dominating the other sensor and is so much better, then the other sensor is actually starting to like really contribute. It's actually holding you back, and it's really starting to contribute noise to the former system. And so we are really doubling down on the vision only approach. And actually in this talk, what I would like to primarily talk about is how we have achieved vision only control without radar, and how we have released this quite successfully so far to the fleet, and what it has sort of taken for us to do that. So here I wanted to show a video, basically showing what the input to the system is. So we have 8 cameras surround, and these are fairly high definition cameras, and we have 36 frames a second. And you can see that basically you can actually understand a lot about this environment from this input. It's extremely information rich. You're getting a huge amount of constraints, 8 million bits roughly of constraints per second on the state of the surroundings. And so it's incredibly information rich compared to any other sensor you may want to have in a car. And so this is the one that we're doubling down on, because this is ultimately where all the difficult sort of scene interpretation challenges lie. So we prefer to just focus all of our infrastructure and development on this, and we're not wasting people working on the radar stack and the sensor fusion stack. We only have one team, the vision team. Now, typically when we talk about vision, the reason people are squeamish about using vision is, and the sort of challenge that almost always is pointed out, is people are not certain if neural networks are able to do range finding or depth estimation of these objects. So obviously humans drive around with vision. So obviously our neural net is able to process visual input to understand the depth and velocity of all the objects around us. But the big question is, can our synthetic neural networks also do the same? And I think the answer to us internally over the last few months that we've worked on this is an unequivocal yes. And I'd like to sort of talk about that. So in particular, the radar API, or like what the radar really gives you, is it gives you a quite accurate depth and velocity measurement. It's a pretty direct measurement of the car ahead of you in very nominal situations. So here I'm showing a random image on the left, and you are seeing the depth, velocity, and acceleration reported by the radar stack for this car. And you can see that it's a bit wiggly on the velocity, so this is some kind of a stop and go scenario. Now, when radar has a good lock on the car in front of you, it's given incredibly good depth and velocity. But the problem with radar is, like, once in a while, at random, it will give you a dumb measurement, and you will not know when that is. And so it's incredibly hard to fuse with vision in our experience. So it might suddenly see a spurious stationary object because of a manhole or because of a bridge, or crossing objects are not very well tracked, or oncoming objects are not very well tracked. And it ends up contributing noise. I'll go into more detail in a bit. But for our purposes, what we want to do right now is we want to match the quality of these predictions using vision alone. So the question is, how can you get a neural net to predict depth, velocity, acceleration directly and do it with a very high fidelity, matching that of radar? So the approach we're going to take, of course, is we're going to treat this as a supervised learning problem, and we need a massive data set of depth, velocity, acceleration on a lot of cars, and we're going to train a large enough neural network and do a very good job at that. That's the standard vanilla approach, and that actually works really well if you do it properly. So here's what it took. So the first component that you need is an incredibly good data set. So, and when I talk about a good data set, I believe it has to have 3 properties that are critical. It has to be large in millions of examples. It needs to be clean. So in this case, we have to have a very clean source of depth, velocity, and acceleration for all these cars. And it must be diverse. So we're not just talking about a single, driving clip of going forward on a highway. We really have to get into the edge cases and mine all the difficult scenarios. And I'm going to show you some examples. And when you have a large, clean, diverse data set, and you train a large enough neural network on it, what I've seen in practice is, in the words of Ilya Sutskever, success is guaranteed. And so let me show you some examples of that. So first of all, how are we going to achieve this data set? So of course, we need to collect training data. The typical approach might be to use humans to annotate cars around us in 3 dimensions. What we found actually works really well is an auto-labeling approach. So it's not pure humans, just like annotating cars. It's an offline tracker, as we call it. And it's an auto-labeling process for collecting data at the scale that is necessary. So we need, again, millions of hard examples. So this is where the scale comes from, is that it's not labeled purely by humans, although humans are involved, it's labeled automatically. So here's an example of some automatic labels we were able to derive for cars on the highway. And the way you do this is, because you are offline and you are trying to just annotate a clip, you have a large number of benefits that you don't typically have if you're at test time under strict latency requirements in the car. So you can take your time to fully figure out exactly all the objects and where they are. You can use neural networks that are extremely heavy. They are not deployable for various reasons. You can use benefit of hindsight because you know the future, not just the past. You can use all kinds of expensive offline optimization and tracking techniques. You can use extra sensors. In this case, for example, actually radar was one of the sensors that we used for the auto labeling. But there's actually a massive difference between using radar at test time and using it in the offline tracker. And that is that at test time, a radar can just report a stationary track immediately in front of you, and you have 20 milliseconds to decide if you're gonna brake or not. If you're offline, you have the benefit of hindsight. And so you can do a much better job of calmly fusing if you really want to. And so there is a massive difference there. And in addition, you can of course involve humans, and they can do cleaning, verification, editing, and so on. And so we basically found that this was a massive lever to allow us to reach the scale and the labeling quality. And then to get the diversity, that was also a massive fight. So here's some examples of really tricky scenarios. So here there's some, I don't actually know exactly what this is, but basically this car drops a bunch of debris on us, and we maintain a consistent track for the label. And of course, if you have millions of labels like this, the neural net, if it's a powerful enough neural net, will actually end up learning to persist these tracks in these kinds of scenarios. Here's another example. There's a car in front of us, and I actually am not 100% sure what happens in this case, but as you'll see, there's some kind of a dust cloud that develops here and briefly occludes the car. But in the auto labeling tool, we are able to persist this track because we saw it before and we saw it after, so we can actually stitch it up and use it as a training set for the neural net. Here's one more example of an adversarial scenario from heavy snow. Again, we can auto-label this fine and create a large collection of examples. Now, as we were working on this over a duration of, I want to say, of roughly 4 months of really just focusing a lot of the team on this problem of achieving really good depth, velocity, and acceleration, we've ended up developing 221 triggers manually that we were using to source data from our customer fleet. And this is just an example, some examples of the 221 triggers that were used to collect all of these diverse scenarios. So for example, we have shadow mode, where we deploy a neural network that is pretty good at predicting depth and velocity. And what we do is we run it silently in the cars of our customers, but it's not actually connected to control. What's driving is the legacy stack. But we're basically running the new measurements of depth and velocity, and we're, for example, looking at whether or not they agree or disagree with the legacy stack or with the radar. We're looking for other sources of jank, like for example, if there's bounding box jitter, detection jitter, the main and the narrow camera disagree. We predict that there's a harshly decelerating object, but the person seems to not mind. All kinds of disagreements between different neural network signals. And there's a long list here. It took us a while to actually perfect these triggers, and all of them are iteration, and you're looking at what's coming back, you're tuning your trigger, and you're sourcing data from all these scenarios. So basically over the last 4 months, we've done quite extensive data engine, and we've ended up doing 7 shadow modes and 7 loops around this data engine here, where on the top right is where you begin. You have some seed data set, you train your neural network on your data set, and you deploy the neural network in the customer cars in shadow mode. And the network is silently making predictions. And then you have to have some mechanisms for sourcing inaccuracies of the neural net. So you're just looking at its predictions. And then you're using one of these triggers, like I described. You're getting these scenarios where the network is probably misbehaving. Some of those clips end up going to unit tests to make sure that we, even if we're failing right now, we make sure we pass later. And in addition, those examples are being auto-labeled and incorporated into a training set. And then as a asynchronous process, we're also always data cleaning the current training set. And so we spin this loop over and over again until the network basically becomes incredibly good. So in total, we've done 7 rounds of shadow mode for this release. We've accumulated 1 million extremely hard, diverse clips. And these are videos. So these are, you should roughly think about, say, 10-second clips, 36 FPS, something like that. In total, we have about 6 billion objects labeled cleanly for depth and velocity. And this takes up roughly 1.5 petabytes of storage. So that gives us a really good data set. Of course, that by itself does not suffice. So we have an incredibly good AI team that is designing the neural network architecture. There's basically the layout of the synthetic visual cortex in order to efficiently process this information. So our architecture roughly looks like this. We have these images coming from multiple cameras on the top. All of them are processed by an image extractor, like a backbone, like think ResNet kind of style. Then there's a multicam fusion that fuses the information from all the 8 views. And this is a kind of a transformer that we use to fuse this information. And then we fuse information first across all the cameras and then across all of time. And that is also done either by transformer, by recurrent neural network, or just by three-dimensional convolutions. We've experimented with a lot of kind of fusion strategies here to get this to work really well. And then what we have afterwards, after the fusion is done, is we have this branching structure that doesn't just consist of heads, but actually we've expanded this over the last year or so, where you now have heads that branch into trunks, that branch into terminals. So there's a lot of branching structure. And the reason you want this branching structure is because there's a huge amount of outputs that you're interested in, and you can't afford to have a single neural network for every one of the individual outputs. You have to, of course, amortize the forward pass for efficient inference at this time. And so there's a lot of feature sharing here. The other nice benefit of the branching structure is that it decouples at the terminals, it decouples all these signals. So if I'm someone working on velocity for a particular object type or something like that, I have a small piece of neural network that I can actually fine tune without touching any of the other signals. And so I can work in isolation to some extent and actually get something to work pretty well. And then once in a while, so basically the iteration scheme is that a lot of people are fine tuning, and once in a while we do an uprev of all of the backbone end to end. And so it's a very interesting sort of mechanism because we have a team of roughly 20 people who are, I would say, training neural networks full time, and they're all cooperating on the single neural net. And so what is the workflow by which you do that is pretty fascinating and continues to be a challenge to actually design efficiently. So we have a neural network architecture, we have a data set. Now training these neural networks, like I mentioned, this is a 1.5 petabyte data set, requires a huge amount of compute. So I wanted to briefly give a plug to this insane supercomputer that we are building and using now. For us, computer vision is the bread and butter of what we do and what enables the autopilot. And for that to work really well, you need a massive data set. We get that from the fleet, but you also need to train massive neural nets and experiment a lot. So we've invested a lot into the compute. In this case, we have here a data set, we have a cluster that we're just building that is 720 nodes of 8x A100s of the 80 gigabyte version. So this is a massive supercomputer. I actually believe that in terms of flops, this is roughly number 5 supercomputer in the world. So this is actually a fairly significant computer here. We have 10 petabytes of hot tier NVMe storage, and it's also an incredibly fast storage. So I believe 1.6 terabytes per second. This is one of the world's fastest file systems. And we have also a very efficient fabric that connects all of this. Because of course, if you're doing distributed training across your nodes, you need your gradients to be synchronized very efficiently. And of course, we are reading all of these videos from the file system, and that requires a really fat pipe as well. So this is a pretty incredible supercomputer. So this is a GPU cluster. Next up, we're really hoping that we're currently working on Project Dojo, which will take this to next level, but I'm not ready to sort of reveal any more details about that at this point. What I would like to do is I would like to just briefly plug the supercomputing team. They've been growing a lot. And so if high performance computing for this application and for training these crazy neural networks excites you, then we would definitely appreciate more help. So please contact the supercomputing team at supercomputing at Tesla to help us build these clusters. On the left here, we have the compute nodes, and on the right, this is a network switch, actually. So the wires here is kind of like the white matter of this synthetic cortex, I guess. The other thing I wanted to briefly talk about is I wanted to also mention briefly that this effort basically is incredibly vertically integrated in the AI team. So as I showed you, we own the vehicle and the sensing, and we source our own data, and we annotate our own data, and we train our on-prem cluster, and then we deploy all of the neural networks that we train on our in-house developed chip. So we have the FSD computer here that has 2 SoCs, FSD chips here, and they have our own custom NPU neural processing unit here at roughly 36 TOPS each. And so these chips are specifically designed for the neural networks that we want to run for FSD applications. And so everything is very vertically integrated in the team. And I think that's pretty incredible because you get to really co-design and engineer at all the layers of that stack. And there's no third party that is holding you back. You're fully in charge of your own destiny, which I think is incredibly unique and very exciting. And then we have a deployment pipeline here where we take these neural networks and we do a lot of typical graph optimization, fusion, quantization, threshold calibration, and so on, and deploy it on our chip. And and this is in the customer's cars, and these neural networks run there. So now what I'd like to show is, I first would like to show some qualitative examples of some of our results in terms of the depth and velocity predictions that we were able to achieve by putting all of these pieces together and training these networks at scale. So the first example here, I have a video where This is on track testing. So this is an engineering car, and we asked it to slam on the brakes as hard as it possibly can. So this is a very harsh braking here in front of us. Even though it doesn't look like that in the video, this is very harsh braking. So what you can see on the right here is you can see the outputs from the legacy stack, which had radar vision fusion, and from the new stack, which is vision alone in blue. So in the orange legacy stack, you can actually see these track drops here when the car was braking really harshly. And basically the issue is that the braking was so harsh that the radar stack that we have actually ended up not associating the car and dropping the track and then reinitializing it all the time. And so it's as if the vehicle disappeared and reappeared like 6 times during the period of this braking. And so this created a bunch of artifacts here, but we see that the new stack in blue is actually not subject to this behavior at all. It just gives a clean signal. In fact, here, there's no smoothing, I believe, on the blue signal here. This is the raw depth and velocity that comes out from the neural net, the final neural net that we released with about 3 weeks ago. And you can see that it's fairly smooth here. And of course, you could go into the radar stack and you could adjust the hyperparameters of the tracker, like why is it dropping tracks and so on. But then you are spending engineering efforts and focus on a stack that is like not really barking up the right tree. And so it's better to, again, just focus on the vision and make it work really well. And we see that it is much more robust when you train it at scale than something like this. Here's another example, fairly infamous example of slowdowns when there are cars going below a bridge. The issue here, again, is that the radar does not have too much vertical resolution. So radar reports a stationary object in front of you. It's as if like the radar doesn't know that there's like a stationary car in front of you or if it's the bridge above. It cannot differentiate those two. So radar thinks that there might be something stationary in front, and it's just like looking for something in vision to tell it that it might be correct. And then we create a stationary target and brake. And so in this case, in the legacy vision predictions, which were already producing depth and velocity, but because we were using radar, the vision inaccuracies were being masked because your bar is only at radar association. Your bar is not at actual driving. And so the depth and velocity were not held up to a high enough bar. And so basically what happens is vision reports for a few frames, reports a slightly too negative velocity for the car. And then it associates to the stationary object. And the stack is like, oh, that must be the stationary thing. And then we brake. And so this, of course, is much cleaner. And you see that the new stack does not see this at all. And there's no slowdowns in this case. Because we just get the correct depth and velocity, and vision obviously has the vertical resolution to differentiate a bridge from a car and whether or not the car is slowing or not. So again, you could go into the radar stack or the sensor fusion stack, and if you have an improved depth and velocity, you could change the fusion strategy. But again, you're just kind of like doing dead work. Like this signal is so good by itself. Why would you do that? So in this setting now, we've improved the situation quite a lot. Here's another last example. We have a stationary approach. Again, this is in track testing environment. This is an example of a test that we would run. And we are just approaching this vehicle and hoping to stop. What you see in orange in the legacy stack is that it actually takes us quite a bit of time for us to start slowing. And basically what's happening here is that the radar is very trigger happy and it sees all these false stationary objects everywhere. Like everything that like sticks out is a stationary target. And radar by itself doesn't know what actually is a stationary car and what isn't. So it's waiting for vision to associate with it. And vision, if it's not held up to a high enough bar, is noisy and contributes sort of error. And the sensor fusion stack just kind of like picks it up too late. And so again, you could fix all that, even though it's a very gross system with a lot of if statements and so on, because the sensor fusion is complicated because the error modes for vision and radar are quite different. But here, when we just work with vision alone and we take out the radar, vision recognizes this object very early, gives the correct depth and velocity, and there's no issues. So we actually get an initial slowdown much earlier. And we've really like simplified the stack a lot and as well. So just speaking very briefly to the release and validation, we've extensively validated this before we, of course, ship this to customers. Just some example numbers for the validation itself. We've handpicked about 6,000 clips in about 70 categories of scenarios like harsh